A last thing we might be asked to do with our electric potential is to plot the electric potential as a function of R. So let's ask, what is the potential at all the different places? So what is the electric potential at R equals 0? So for that one, we can use our expression for electric potential inside. The electric potential inside would be given by K times Q over 2R times 3 minus 0 squared, because R is 0, divided by the radius squared. So that would be 3 over 2 times KQ over R. So there's the electric potential right at the center of the sphere. That's already kind of interesting compared to the electric field, which was always 0 right at the center because there was no charge inside. What is the electric potential if R is less than the radius? Then that's the expression we got right here. So K times Q over 2R times 3 minus R squared divided by R squared. And then we have what is our electric potential at the surface, R equals R. To find that, we could plug our R into this equation. So we get 3 minus radius squared over radius squared would be 3 minus 1, which would be 2. That 2 would cancel with this 2 and give us KQ over R. Or we could recognize it that we did that at the beginning part of this problem and we asked for the electric potential at the surface and we found that it was KQ over R. And we'll ask, what is the electric potential outside the surface of the sphere? So that was the first part we did. And we saw that it was KQ over R. So just like a conductor and just like the point charge, the electric potential is the same when it's an insulator. So we get KQ over R, like a point charge. So now we can plot this if we wish, beginning at R equals 0 and going out to far away. So we'll do a plot of the potential as a function of distance from the center versus R. So at the very beginning, our biggest value is right here. That's 3 over 2 times KQ over R. Then it goes as minus R squared, so it starts to decrease. Looks something like this, a little bit hard to draw. Right at the surface, this value right here is KQ over R. Then as we go far away, it dies off as 1 over R. So we switch to a curve that kind of dies away like this. And then we might want to, just for interest's sake, compare the potential graph with the electric field graph. So inside the electric field of a conductor, we had that it increased linearly with respect to distance from the center. And that was the expression we wrote down right here when we started our potential. It was KQ times distance from the center over the radius cubed. So electric field starts at 0 and goes up linearly. So electric field is proportional to R when you're inside. Then outside it dies off more quickly than the potential because it goes as 1 over R squared. So there is a comparison between the electric field and the electric potential, and we definitely see that those are not the same thing.